Now that we have these new functions, sine and cosine, we could ask what are their derivatives. So if we want to take the derivative of cosine, remember cosine is just e to the t plus e to the minus t all over 2. Of course, the 2 is just a constant, so I could pull it out and work on taking the derivative with respect to t of e to the t plus e to the minus t, which would give me, let's see, 1/2 times the derivative of e to the t is e to the t, and the derivative of e to the minus t is minus e to the minus t. If I look at that, then I see that we have really e to the t minus e to the minus t all divided by 2, which is the hyperbolic sine, or the sine. So the derivative of the cosine is the sine, and the derivative of the sine, if we take the derivative of e to the t minus e to the minus t over 2, same procedure here. We take the derivative of e to the t, we get e to the t again, and we take the derivative of negative e to the negative t, and we get plus e to the negative t, which is back to the hyperbolic cosine, or the cosine. So the derivative of the cosine is the sine, the derivative of the sine is the cosine. That's very close to the case with the elliptic trigonometric functions, except for the derivative of the cosine is the negative sine. So if you don't have the h, then you get a change in sign. We have sine and cosine. We could build new combinations. What would be good names for these? If I took the sine divided by the cosine, natural name for that would be the hyperbolic tangent, or the tangent. And if you took the cosine divided by the sine, that should be the cotangent, or the hyperbolic cotangent. And 1 over the cosine, we ought to call that the hyperbolic secant, or the secant. And this should be the hyperbolic cosecant, or the cosecant. Now, what would their derivatives be? Well, the derivative of the hyperbolic tangent, or the tangent, we could get that from the quotient rule. Remember, since tangent is sine over cosine, we take the derivative of the top. The derivative of the sine is cosine, times the bottom, which is cosine, minus the top, which is sine. And the derivative of the bottom, the derivative of the cosine, is the sine, all over the bottom squared, so over the cosine squared. Remember, cosine squared minus sine squared, that's what we have on top, and that's equal to 1. So we have 1 over the cosine squared, which is equal to the hyperbolic secant squared, or the secant squared. So that's a lot like what happens with the tangent. The derivative of the tangent is the secant squared. The derivative of the hyperbolic tangent is the hyperbolic secant squared, or the derivative of the tangent is the secant squared. Something similar happens if you go to take the derivative with respect to t of the hyperbolic cotangent. You get, using this definition, you get the derivative of the top, which would be sine, times the bottom, which is also sine, so you get sine squared, minus the top, which is cosine, and the derivative of the bottom is also cosine, so we get minus cosine squared, all over the sine squared. Let's see, cosine squared minus sine squared is 1, so if you reverse the order, you'll get the opposite thing. You'll get negative 1, so we get negative 1 over the sine squared. But 1 over the sine is the cosecant, so we get negative cosecant squared of t. Okay, let's do it for the secant. Now, if we're taking the derivative of the secant, we could think of that as we're taking the derivative of the cosine to the negative 1. We take the derivative, the negative 1 comes down, and we get cosine to the negative 2 times the derivative of what's inside. The derivative of the cosine is the sine. So we end up with a negative sign, and we have a sine over cosine and another cosine downstairs. So 1 over the cosine would be the secant, and then we have a sine over cosine left. That would be the tangent. So this one's just a little bit different. The derivative of the secant is the secant tangent, but the derivative of the secant is the negative secant tangent. So we get an extra negative sign. It's kind of messed up because the derivative of the cosine is just the sine, not the negative, so that messes up the secant as well. Let's see, we can do the cosecant, the derivative of the cosecant since the cosecant is the sine to the negative 1, take the derivative and we get negative sine t all to the negative 2. The power comes down, we get the power to 1 power less, and then we take the derivative inside. The derivative of sine is the cosine. So we have negative, we've got a cosine upstairs, and we've got two sines downstairs multiplied. So cosine, or 1 over the sine, that would be the cosecant, and cosine over sine would be the cotangent. So the derivative of the cosecant is the negative cosecant cotangent. So we've got the patterns are pretty similar to those for the elliptic sine and cosine, the regular sine and cosine. The only variations are right here in the secant, and then of course the derivative of the cosine is just the sine, whereas the derivative of the cosine is the negative sine. So other than that, we have these same patterns for these functions that are defined in a similar way. So let's maybe apply this. Let's say someone asked us to take the derivative of 2 root t times the hyperbolic tangent of root t. First we need to use the product rule, so we take the derivative of the first. Let's see, this is like 2t to the 1/2 times the hyperbolic tangent of t to the 1/2. That will help me if I take as I take the derivative. The derivative of the first, then the 1/2 comes down and just gives me t to the negative 1/2, because the 1/2 cancels the 2. And then we have times the hyperbolic tangent of t to the 1/2. And then we'd have the first, which is 2 root t, times the derivative of the second. The derivative of the tangent is the secant squared. So we get the secant squared of the square root of t, times the derivative of what's inside, and the derivative of t to the 1/2 is 1/2 t to the negative 1/2. So we get a little cancellation here, because t to the negative 1/2, that's 1 over the square root of t. That's going to cancel t to the positive 1/2, right, or the square root of t. And this 1/2 will cancel that 2. So we get 1 over root 2, that's t to the negative 1/2, times the hyperbolic tangent of the square root of t, plus the secant squared of the square root of t. If we need to go backwards, here's one that could use a substitution. If I let u be the natural log of t, so I'm doing an antiderivative here, du would be the derivative dt, and I happen to have dt over t right there in the problem, so the problem becomes the antiderivative of the cosecant of u times the cotangent of u du. Okay, and the derivative of the cosecant was the negative cosecant cotangent, so this must be negative cosecant of u plus c, since the derivative of the negative cosecant would be the positive cosecant cotangent. Now I just have to substitute back, and we get the cosecant of the natural log of t.